The early ancient Greek ballista was developed from two weapons, called an oxybellies, a composite bow on a stand, and a gastrophetes, a handheld crossbow. After 146 BC and the invasion of the Greeks by the Romans, Greek technology, especially these proto-ballista designs, were spread and improved upon at a rapid rate. In 55 BC, in the Roman conquest of Gaul by Julius Caesar, the heavily modified Roman ballista design was an integral part of warfare, especially sieges, where the high-speed projectiles could fly accurately and destroy both rudimentary and, more slowly, advanced defenses, such as the thick walls seen in Masada. In addition, once fired, the ballista bolts would deform and could not be used as projectiles by the enemy, as some harder stones from catapults could be. Here's a custom-made animation showing the design and functionality of a Roman ballista. As you can see, the ballista uses tension built up in the ropes to launch bolts at high speeds. The ballista was basically an oversized mounted crossbow. Historical evidence shows that the ballista were used by the Romans at the siege of Masada. However, the TV movie miniseries Masada did not feature any ballistae. While catapults, which were the only siege engine shown in Masada, were used in Roman warfare, they were not exclusive, which is how they are portrayed in the movie. Ballistas, however, did not only fire bolts. In fact, slight modifications to ballista could allow it to throw stones and other projectiles. These modifications to the ballista earned the name carroballista, and these engines could wreak havoc on enemy fortifications, which is why they were used so often. In addition, sniping with the ballista was common. Smaller models could pinpoint and pick out one commander and only shoot him, which was very useful. All this talk of projectiles got me thinking, how much damage did a ballista usually do? Well, with no spare ballistas just lying around, I decided to use the second best thing, physics. Here's the rundown. To find the amount of stuff thrown out by the impact, called the ejecta, we need one thing, the energy. First, however, in order to get energy, we need the mass and velocity of the impact. Easiest is the mass. An average projectile mass for a siege ballista was about 45 kilograms. Yeah, I know it's metric, and yes, I know I didn't convert it, but this is science, and we use real units. Now that we have the mass, we need to calculate how much energy the projectile has. And to do that, we need to know how fast it comes out of the ballista. This is where it gets hard. The force that will push the projectile out of the ballista is stored in these two ropes, each storing an equal amount of tension. Now, to find out how much force is in each rope, we need to use a couple formulas. First is the relation of Hooke's law to Young's modulus. I don't have time to explain both, but basically they describe how tension works. The relation is K equals Y times A over L, where K is the spring constant, Y is the value in gigapascals from Young's model, A is the area of the rope, and L is the initial length of the rope. Now we just plug in these values. The Young's modulus constant is 35 gigapascals. The length of a rope is about 1.4 meters, and the area of the rope is 1.5 centimeters squared times pi, or about 7 centimeters squared. So, 35 times 7 divided by 1.4 equals 175. The units for this is newtons per meter, or Newton meters. Now that we have solved for K, we can use this in Hooke's law, which determines the force, and that's pretty simple. Since the draw ballista coils about 1.2 meters of rope, that's the change of distance that we plug into the formula. F equals negative K times the change in the rope length. Since we know that K is 175, we are changing the length of the rope by negative 1.2 meters. We can calculate that the force is 210 newtons in both directions, pulling back, and what would be pushing forward on the projectile when it leaves the ballista. This means that each rope arm has about 105 newtons of force in it. Thanks to Newton, we know that force is equal to mass times acceleration. Therefore, 210 newtons equals 45 times the acceleration, so the acceleration has to be 4.6 meters per second squared. Now that we know how fast it was launched, we can use the first kinematic equation to determine the final impact velocity. The equation is final velocity equals start velocity plus acceleration times time. The acceleration is 4.6 meters per second squared, and the start velocity is 0, since it's not moving when we start. Here's another assumption. From my arbitrary judgment, I'm going to say that the best time for flight is about 5 seconds. Plugging all this in, we're going to get about 23 meters per second as the final impact velocity, which is about 51 miles per hour, which is pretty reasonable. To calculate the amount of energy in the projectile, we use the equation E equals 0.5 times the mass times the velocity squared. The mass is 45 and the velocity is 23. In final, we get 11,902.5 joules. Plugging all this into an online calculator, we get the crater diameter of 1.28 meters, or just over 4 feet from rim to rim. The depth is approximately 0.89 meters, so in about 4 shots the extremely thick walls of Masada would be breached, assuming that the walls of Masada are very dense and structurally strong, which they were. In summary, a ballista was a formidable war machine. It could do serious damage to both armies themselves and the fortifications that protected them. Here are my sources.